Okay, maybe should we begin already? It's 6 p.m. here. I don't know what time is there. Oliver, are you in Japan, right?
It's 1 o'clock in the morning.
Okay, good time for a seminar. At least for a seminar where you are the speaker. It should be worse if you were only the attendee, but never mind.
I can stay awake because I'm speaking. Don't worry.
Okay, okay. Well, given that I closed the page of the seminar, I cannot read your biography, but just I want to say that I was really impressed that you studied in Oxford and you did your PhD in Cambridge. It's right that?
Yeah. Yes. Don't be impressed, please.
Well, I'm really impressed, but in any way, I'm really impressed for all your career. You are already a classical in physical acoustics, so that at least it happens to me that when I try to learn something related with laser ultrasonics or picoseconds ultrasonics, your name appears everywhere. And also it's happening as well in the metamaterials domain. And I guess that is the main topic of the talk today, right?
That's right.
Okay, so that...
Thank you.
You can begin when you want.
Okay. You heard, actually, Daniel's heard the first half of this talk, but please bear with me, Daniel, and the second half is something you didn't hear yet. So, yeah, so thank you very much for the introduction. Is everybody able to see the screen?
Yep.
Yeah? Okay, so I'm signing in from Hokkaido, the northernmost island of Japan. And today, the subject of my talk is maze. It's a rather strange title, but they're somewhat unconnected. The two topics, maze balls and Foxonic metamaterials. However, they both are related to acoustic metamaterials, and that's the common element of this talk. And I also have been recently affiliated with Osaka University, but at the moment I'm not in Osaka. I'm in Hokkaido University at the moment. So, but not at this very moment in time where I'm just in my house. That's obvious, I think. But, and so this is the first page of the talk, and there are a couple of nice pictures, one from each subject of the title, which I'll be telling you about soon. And I did mention that this was the northernmost island of Japan, but the season is wrong, but I just show you what it's like. I usually do this in all my talks because I'm a kind of winter sports enthusiast. I show you what it's like in winter, and it's very nice like this. And so, without further ado, this is what I want to talk about. A very, very quick, firstly, a very, very, very instantaneous review of acoustic metamaterials, and then the two subjects in question. So the maze ball is used for sound blocking, and so it's written maze ball sound blocker. And then I want to introduce this new type of metamaterial called a Foxonic metamaterial. So I'd like to first thank these people for helping with the maze ball subject, which was heroically mostly carried out by Ting Zhang from the Nanjing University of Information Science and Technology, who visited us. And also my colleagues at Hokkaido University and colleagues from China. So this is a Japan-China collaboration. Okay, so this is the lightning review of acoustic metamaterials, but there is going to be a less instantaneous review of acoustic metamaterials halfway through the talk. So I'm going to do it gradually, because if I did it all at the beginning, it would be heavy duty. So this is acoustic metamaterials in 30 seconds. So there are two things to say about acoustic metamaterials. You can have effective density, it's written here, how to make an effective density. A simple way is to put a mass inside a mass. So if you shake this ball, which is just standing on a support here, you can feel the mass inside moving. And if it doesn't move in phase with your hand, it's going to create what could be even negative density. That's what this is actually a meta atom, because it's a single element of a metamaterial, which is a resonant, deeply sub-wavelength unit. So it's an oscillator which is deeply sub-wavelength. At least the oscillator and the spacing between adjacent oscillators, if there's more than one, has to be deeply sub-wavelength. Then another type of element is effective modulus element. This is an effective modulus element. An example of one is just a hinges here, a couple of springs if you want to join it to another one, and a couple of masses. And this thing is like going to resist compression or expansion. So it's an effective modulus. And if you get the phase right, again, you can get negative modulus happening. So this is also very important to acoustic metamaterials. Although today won't be such, well, actually today both of these are important, both of these are important, modulus and density. Okay, so it was a little bit more than 30 seconds, but it was pretty instantaneous, only 2 slides. And so that's enough to make a background for the maze ball sound blocker. Okay, I'll introduce you slowly to the subject of labyrinthine metamaterials, which is maze-like metamaterials in the field of acoustics. So what is a maze ball? If you ask somebody who's aged 10 or less what a maze ball is, they will probably tell you about this type of thing, which is a children's toy. Well, it's pretty obvious what it is. It's just a maze, but in the shape of a ball. You can have ones like this where you move a little steel ball bearing over a surface, or you can have this fiendishly complicated ones where you move a steel ball bearing through all sorts of obstacles by the correct rotation of this object. But actually, this is absolutely nothing too much to do with an acoustic maze ball. But this is what you'd look on the web, you'd find if you searched for maze ball. But so a maze ball is an example of a space coiling metamaterial, which I mentioned as a labyrinthine structure. And this was introduced at first by Jensen Lee from the City University of Hong Kong. And they proposed that if you made this structure, which is a kind of mazes joined together, but there is a path through the maze from one side to the other, then this thing behaves like a slow sound velocity material. So because it takes the sound so long to get through the maze, it has an effectively slow sound velocity. And so they showed that you could do things like effective negative refraction of acoustic waves. And then this was further taken up as an idea by Steve Kummer at Duke University in the experimental regime. And this was actually verified in experiment at 2.1 kilohertz, that you could have negative refraction and density near zero, and even large refractive indices. Of course, negative and very highly positive. And there the subject lay for a while. And after that, there was a proposal to make a maze cylinder, This is a cross-section of the maze cylinder, and this is the maze cylinder, which was about 100 millimeters in diameter. And you can see there's a path from the inside to the outside. So they found that if they put this cylinder inside a duct, even though it only blocked 15% of the volume, if you take a cross-section, 2 cross-sections either side of the cylinder in the duct, it only blocked 15% of the volume, but they managed to find that it could block a significant amount of transmission. when this thing resonated. And then this is 2015, and then 2 years later, the maze ball was proposed. And this is a maze ball. It looks like a, if you weren't familiar with maze balls, you'd say this was a bowling ball, because bowling balls have famously got holes in them like this to grip them. But firstly, the diameter of their maze ball was a bit smaller than a bowling ball, much lighter. And secondly, bowling balls aren't filled with a maze. And this was filled with a maze, but this is a fiendishly complicated maze ball. It's icosahedral symmetry. There's 20 holes in it. And the filling factor, when they put it in a waveguide, was 40%. It filled up 40% of the volume. And also they found it could block sound pretty well. So, our objective was to try and do a little bit better on this maze ball front and make a more simplified maze ball and look at simpler geometries that would give simpler resonance symmetries. So when you learn about resonances of even a resonance of a plane sphere or a plane spherical cavity, you can have a mode which is just expansion and compression, which you call the monopole mode. You have a mode where there is movement backwards and forwards, and this is called the dipole mode. But people are also interested in more complicated motions. Well, going on the same series, you'd have a quadruple mode, and you'd have an octopole mode. And then in general, you'd have a multipole mode. So you can't get a dipole mode so easily with this thing, because it's 20 different cavities all connected together. But it would be fun to find a simpler maze ball, which demonstrated simpler symmetry of its vibrational normal modes. And so our metamaterial maze ball design, we call it a metamaterial because the frequencies we're interested in correspond to wavelengths much larger than the ball diameter. We choose a ball diameter of about 90 millimeters, and we're interested in wavelengths longer than that, acoustic wavelengths in air, much bigger than that. And you see here a cross-section of the maze ball. It's got a hole in the center. It's got a sphere in the center connected to a little hole. And then to get to the outside, you have to go through this winding labyrinthine passage like this. And finally, you can get to the outside. So the sound takes a long, long way to get out. In fact, 5 times longer it takes in length to get out by the shortest route compared to the direct route from across the radial direction. So actually, that means that you expect the effective sound velocity to be 5 times smaller than the real sound velocity. So one thing that this means is that any resonance of this maze ball will be 5 times lower than you expect for just a hollow sphere of the same diameter. So you can make lower sounds with a maze ball than you can with a hollow sphere of the same size. Okay, and then this one, it looks like this. It's got 8 holes, and they all connect to the center. And you can actually, as I mentioned, model this by a slow sound velocity, connecting the inner hole and the outer hole. And these blue areas have effective low sound velocity. Now, this maze ball can be made by 3D printing. Okay, so that's what, in fact, we did. So how to make this really complicated object? Well, you print the parts of the maze ball and then assemble it by gluing the parts together. So you make 1/8 of a maze ball by gluing 3 pieces together, and then you have to, before you assemble it, you have to get rid of these little strands which come out partly necessary to hold the thing together while it's 3D printing, but Once it's finished printing, you have to cut them off, but that's not difficult. And then you just stick this thing together, and each this thing is a unit that is actually sealed around the edges, except for this hole at the top and the hole at the bottom. So it's not connected to the other 8 bits that you assemble together. So it's independently acting 8 different sections. And actually there's some mirror symmetry between adjacent ones. It's a bit complicated, but it all fits together beautifully like this. And I wanted to see what it was. We made, Ting Zhang made a lot of these maze balls, and she gave me permission to destroy one. So I took a saw and I've cut one in half, and you can see what it looks like from the side here. You can see that they're all sealed, but I just peeled away the thin layer here, and you can see that you can't see the hole because it's behind, but the way it's interconnected is pretty obvious here. And you can see the little hole and the cavity in the center. So there's a maze ball. And if you go to a numerical finite element program like COMSOL, you can figure out what the normal modes are if you're at atmospheric pressure. And by the way, I'm just making sure everybody can still hear me. It's okay?
Yes.
Okay, because there's no sound of coughing or, you know, somebody cough now and again, please. Okay.
Yes, we do.
Okay. Everybody's there because you never know. Last time I was giving this talk, the internet cut out and I probably kept on talking for many minutes. So I hope that doesn't happen. Okay, so these are those modes I just mentioned, the ones that have this nice symmetry, the simplest symmetry. So this mode is like just expanding and compress and contracting. And this is the dipole mode. The far field pattern means that at this resonant frequency, it's actually disturbing the sound all around and emitting, if you like. And so it makes this far field patterns. And it's clearly mono mode, dipole, quadruple, and monopole, sorry, and quadruple and octopole. So these kind of beautiful patterns you can see. And each one has a different, what should we say? Yeah, well, I don't really know. A characteristic wavelength associated with the frequency, of course, which is around 30 centimeters. And these 3 are very similar in frequency, interestingly, just a little bit different in frequency. This one is a bit separated in frequency. Okay, so this is where I explain that these are in a way harmonics, okay, harmonics. So the best way to explain harmonics to people, if you don't have a wine glass with you, or if you don't have a trumpet with you or a flute or something, if you just bring your vocal cords and you want to show people harmonics, then the best way is to sing a Mongolian song. Well, I don't know how I managed to learn this, but in Mongolia, they have this nice violin called a morin khur. And when you're playing the morin khur, you have to sing at the same time a homi. And a homi is a song where at the same time when you sing with 2 different tones, okay? Basically a main tone and an overtone. So what you're seeing on the screen here is like the main tone and the overtone. And I'll just try and sing a homi to give you an idea of that. Yeah. So it's a bit like this. Not sure whether you heard the overtone, but definitely there's a harmonic there. Okay, so having explained what harmonics are, let me first go to the monopole resonance. And we're going to put our maze ball inside a waveguide, because the previous workers put their labyrinthine devices, sometimes cylindrical, sometimes spherical, inside waveguides to see how much sound you could block, because this is potentially good for blocking sound. And if you do this with COMSOL, you can figure out, if you ignore viscosity, what you expect to happen on resonance. So, well, you have to choose the orientation of your ball, which for the monopole resonance is not critical at all, but just for the sake of example, you have to choose an orientation. We put the hole facing the oncoming sound. Below the resonance, as you see from the left-hand figure example here, the sound is almost undisturbed, passes around the ball, and is transmitted almost 100%. The same goes for above the resonance. However, on resonance, which is shown in the animation, this blocks virtually all the sound. In fact, it reflects 100% of the sound. And the resonant frequency predicted is 634 Hertz, which, if you compare with what we discovered was true in empty space, not far off, because here it was 631 Hertz. So putting this sphere inside a 200 millimeter diameter waveguide, which the sphere is about half the waveguide diameter, the diameter of the sphere, so not too close to the walls, but it just changes the resonant frequency a tiny bit, but it blocks all the sound. So this is very interesting. On resonance, it blocks the sound. Okay, the resonance is going to produce a wave out of phase, which cancels the transmitted wave. In fact, that's what happens. Okay, so that's the monopole resonance. And if you want to see other types of animation of this resonance, you can take a cross section through the waveguide in a horizontal plane and plot the acoustic pressure, and it looks a bit like this. So nothing's transmitted, standing wave in front of it. And then if you want to take a slice in the vertical plane to see what's happening inside the maze ball in more detail, you can see there's a very strong pressure enhancement inside the maze ball. And these arrows show the direction of the acoustic velocity at some points inside the sphere. So you can see it's oscillating. And there's also a region here where the intensity is almost zero because of the standing wave. So I just put a few facts and figures here on the left-hand side, just to remind you that a lot of power is localized in the maze ball on this resonance, monopole resonance. They're very sparse in a way. It's only filling 13% of this tube if you take the volume around it. And so a 13% volume fraction can block the whole of the sound, which is quite nice. And the ball is very sub-wavelength, it's lambda over 12. And the pressure enhancement recorded inside this sphere is 45. So it has it's a kind of squashing the sound and making a very high intensity sound right in the center, which is very not so surprising because you're coming in from 8 different directions, but it's quite startling. Okay, so of course the next thing to do is to try to do an experiment. So here is exactly what we simulated. 200 millimeter internal diameter plexiglass tube, hanging a maze ball by fishing line in the center, some microphones here to record the sound pressure before and after. There's channels 1, 2, 3, 4 here. So it's a four microphone measurement. It allows you to determine everything quite nicely. And we chose a frequency range to encompass these main resonances. So this was done in Nanjing. So these are the experimental results. And in the region of 500 to 800 hertz. And instead of being quite as marvelous as the simulations, we didn't include viscosity in the simulations. You might be disappointed with us for not doing that, but actually it would have been very arduous with computer time, because all these tiny labyrinthine channels takes a lot of computing time. And if you include viscosity as well, it becomes very difficult to simulate. So instead of doing the real viscosity simulations, we did an effective viscosity simulation where we just added a loss coefficient to the acoustic propagation instead of a proper viscous Navier-Stokes type thing, you know. But this is what the other people did in the past when they did these simulations, and the result is quite nice, because you see here the reflectance and the transmittance is a function of frequency. There's a dip in the experimental curve, which is the blue dots, and the green curve is the reflectance. So we are losing about 70% of the power instead of 100%, and we're reflecting 20% of the power. And of course, some sound will be absorbed as well, which explains why these two R and T don't sum to 1. There's like 50% of the power is actually absorbed. And to simulate this correctly using this effective model where you include a loss coefficient of the basically you can include it like this, and a complex component in the K vector, and this gamma you just fit it until it agrees with the experimental results. So that is quite successful in quantitatively and phenomenologically explaining these results. Okay, so what's it got to do with metamaterials? To know that, you have to derive the effective parameters, which you can do because it's an effective 1D problem. And using a standard technique to derive the effective modulus and effective density, which I mentioned at the beginning of this talk by those two very crude examples of meta-atoms. But, and I mentioned that effective modulus can be negative, and I mentioned that effective density can be negative. And if you have very little loss, which is this dotted black curve, at this monopole resonance, you expect before the resonance a negative modulus, and then a positive modulus. And at the similar frequency, you also expect a change in the density, but not negative. Okay, it's positive. So you could say that this monopole resonance engenders a negative modulus, which is what I said, because I gave you an example of a negative modulus of a hinge that moves like this. And then I mentioned that a balloon that moves in this breathing mode also has a negative modulus. It's when you have a effective compression or expansion, and exactly what you have in this case of the monopole resonance. And so you expect some kind of effective modulus effect to be strong. Unfortunately, or fortunately, I don't know, in physics, when you do an experiment, you always want it to agree with the theory, but unfortunately, we had more losses than required, than would have been, we have more losses than this black curve. We actually predict this blue curve, which is almost overlapping the red curve, which is the experiment. The blue curve is hidden by the red curve. And the blue curve is the curve based on the losses we observed in the last slide. So then it agrees very well when you put in the numbers with an effective loss coefficient. So the only reason the modulus didn't go negative is because of the losses, but the variation is very similar. And something like what you expect in theory also happens for the density. Okay, so things are more or less explicable for this monopole resonance. How about the other resonances? Okay, so the next one to look at would be the dipole mode. And to excite the dipole mode, it turns out it's better to excite a point on the ball which is not open like this whole part, but equidistant between 4 holes. And this excites very nicely the dipole mode. And the dipole mode, without viscous losses, predicts no sound transmitted at 950 hertz and or 949 hertz. So this is the dipole mode. And if you rotate the ball again to this orientation, you can excite not only the dipole mode, also the quadrupole mode, and a tiny bit the octopole mode. And they're shown by these animations. So these 3 frequencies correspond very closely to the ones that we modeled when the ball was not in the waveguide. Of course, these transmission curves are obtained when the ball is in the waveguide. There are some features here we haven't properly explained. Why is the dipole mode broader than the quadrupole mode, for example? Why is the octopole mode only a tiny bit excited, etc., etc.? But these are things that maybe would be interesting to look at in the future. So so far this is just modeling, okay? What can you do with a maze ball apart from just blocking sound? You can demonstrate the phenomenon of acoustic tunneling, because round the monopole resonance you get negative, if you have very little losses, you get negative modulus, but around the dipole or quadrupole, for example, frequencies, instead you get negative density, because these things are more like the first example of the meta-atom I showed you, which is like a mass within a mass. So in other words, the sound is going backwards and forwards, and that gives you a negative density. And you can also get a 0 density, but when the negative density crosses and becomes positive. And if you look at the 0 density point, it corresponds to the tunneling case. It means there's no resistance to the wave. And so if you compare, here we have just a simulation of a square duct with a bend. Now, if you don't put any balls in this duct, any maze balls in this duct, it transmits quite badly around the bend. I don't know if you can see it here, but the actual amplitude goes down quite a lot around the bend here, although it's not so clear. It depends on frequency a little bit, but when you put 3 maze balls in this corner, 1, 2, 3, I think you can just make them out, then the sound goes around the bend almost unhindered and retains its approximately plane wave character inside the waveguide. So if you choose the right frequencies, which are the density near 0 frequencies, around these multiple resonances, you can get sound tunneling, which is quite famous phenomenon in metamaterial physics. I mean, it's been demonstrated for other meta-atoms, like you can make a hole with a membrane in it, and you can show that the sound goes through as if the wall is invisible. The wall in which the hole is placed is invisible. And there are many different examples of this density near 0. So if you have maze balls, you can play around with acoustic metamaterials quite a lot. You can demonstrate negative density and negative modulus and density near 0 and things like that. So I just got to conclude this first part of this talk that we've seen Me resonances. I didn't mention the name of them, but they're the same as what you get in optics. They're called Me resonances because of small particle resonances are called that, according to the discoverer. And with monopole, dipole, quadrupole, and octopole symmetry, and you can get high reflectance, at low frequency. So because the maze ball is very low sound velocity, then you get low frequencies generated by small objects, which is quite an interesting phenomenon. So you could imagine making a maze ball, which is a much finer maze structure, And if you do your lossless simulation, you probably could have a 1,000 times slower sound velocity effective than the sound velocity in air. And you could have a tiny ball with a very low frequency. And you could hit, it's like hitting a wine glass, and it behaves like a bass drum or something. That's how strange a maze ball is. But in practice, a maze ball is limited by viscosity, so it won't work if you try and do 1,000 times slower. But anyway, we did 5 times slower, which is not too bad. I mean, the other groups that I mentioned who did this maze ball and maze cylinder work all were in this roughly 5 times slower sound velocity regime. Okay, so it's about lambda over 12, and you can show negative mass, and hopefully somebody, if we choose, what should we choose? We could make the ball a bit bigger and actually, if you put it in a smaller waveguide, which would be a good question from a questioner, what's the effect of the ratio of the waveguide diameter to the maze ball diameter? It's very complicated, actually. If you make the waveguide a bit bigger or a bit smaller, sometimes you get this beautiful negative modulus effect, sometimes you don't. So I was just glossed over that fact, but it's actually very complicated how it interacts with the waveguide itself. And that needs more research. And finally, I demonstrated tunneling. So I don't usually go through conclusions this carefully, but today I have 2 topics, and supposedly I'm going to keep my time. So now I'm going to go on to the second topic, which is Foxonic metamaterial. And I'm very glad that, I hope he's still here, our friend and colleague Vincent Laude. Hello, Vincent. Because Vincent Laude and his crew coined this word, Foxonic. So I'll explain this as I'm going along.
Thank you, Oliver. Yes, I'm here.
Yeah, okay. I'm glad you're here. So you're the inspiration for this work. So, and this is again thanks to my friends in Hokkaido University and also Nanjing, and a collaborator from Kyoto Institute of Technology, Tetsuya Ueda, who's provided the inspiration for the electromagnetic part. So, Foxonic metamaterial outline. I'd like to talk about introduction to metamaterials and Foxonic metamaterials, and how to make a Foxonic metamaterial, and our Foxonic metamaterial, which we demonstrate by simulations. So this stuff I'm going to talk about is known to many of you, but so most of it's just reminding you of things you already know, this introduction. But in any case, I will carry on with this, because not everybody always knows everything. So what is a Foxonic crystal? I have to start with Foxonic crystals. And this is a dual photonic and phononic crystal. So the X is replacing the T in photonic and the N in phononic, because it's both at the same time. And this was proposed theoretically by Moldavin at MIT, and then the group at Fem2ST in Besançon, including Vincent Laude, who is here today, actually demonstrated this was actually working in practice, and coined this term Foxonic crystal. What are Foxonic crystals useful for? They can control sound and light, of course, because they're at the same time a phononic crystal and a photonic crystal, which is a periodic electromagnetic structure as well as a periodic acoustic structure. Examples are, in gigahertz acoustics, you can have a Foxonic gallium arsenide superlattice, where you have an acoustic nanocavity surrounded by an optical microcavity. And they're both produced by periodic structures in the respective waves. So this is very good for dual confinement of photons and phonons, and this has been investigated heavily by CNEA Bariloche and CNRS Marcoussis, for example, in this first study here. Another one is example is in cavity optomechanics, where you Caltech group showed that you can combine acoustic and optical photons and phonons, in other words, inside a strip with holes, and thereby achieve cavity optomechanics laser cooling. And even it's been proposed that you can use this sort of structure for chemical sensing. If you look at the change in the optical and the acoustic spectra, when you add mass to this Foxonic structure, you can detect the presence of the adsorbed species. So, which was a study done at the Otto von Guericke University in Magdeburg. So, Foxonic crystal is well known since 2006. So, what about metamaterials? So, I should just do a brief introduction. You know this stuff. Some of if you've been at this seminar for a while. But anyway, you can make negative permeability by use of wire arrays, as proposed by Pendry, and variations of this are this is gigahertz microwave frequencies. Variations of this are metal strips with dielectric. Everything can be translated into the optical frequency regime just by making the wires smaller. Nanowires, for example, as demonstrated in the University of California, Berkeley, by silver nanomers in alumina, for example. And that's negative permittivity. But negative permeability, also introduced by Pendry's group, can be achieved with split ring resonators, which an example of which is shown here, which can be have an inductive response, and in fact they can behave like a little inductor connected to a capacitor, and this is good for making a negative permeability little coil. This has been also translated into the optical regime, notably by a group in the Institute of Nanotechnology in Karlsruhe, for example. And so everybody knows all about this stuff. And if you put these things two together, you get double negative electromagnetic metamaterials. Okay, so you just mix the two together, the wires and the split rings. And you can do it also in the optical region, and you can do it in the microwave region. Okay, so acoustic metamaterials, in the same way, as I mentioned briefly before, you can have single negative, which is mass within a mass, or you can have single negative density, single negative bulk modulus by resonant cavities, which are acting as this kind of expanding and compressing system. For example, in a waveguide here, or you can combine the two together and get double negative acoustic metamaterial. So you can do this kind of thing. Double negative is not limited to electromagnetics. Okay, well, I should mention at this moment that how about all at the same time? How about electromagnetic double negative plus in the same material at the same time acoustic double negative? What would that be called? That would be called an example of a Foxonic metamaterial as opposed to a Foxonic crystal. So that was the thing that I thought might be fun to try and do before, when I first stupidly suggested this subject, thinking that it would be a good way to get grant money. And actually, that wasn't the stupid part. That was the clever part, because actually they gave me the money. So, but the stupid part was having promised to do it and not knowing how to do it. Actually, I promised to do it by combining optical regime electromagnetic metamaterial with gigahertz regime acoustic metamaterial, which is fiendishly difficult. So that was the stupid thing, to promise something really difficult. So, but before that, we should start to think about, again, a little bit more carefully, how to make a Foxonic metamaterial. And I didn't really tell you enough about negative density, not properly. And also, I should have mentioned that you don't have to have a quadruple negative Foxonic metamaterial to prove you made a Foxonic metamaterial, because a Foxonic metamaterial could be single negative electromagnetic, for example, and single negative acoustic. You know, you don't have to go for gold from the very beginning. Okay, so I better just briefly say what is a effective negative density. But before that, I should mention a little bit more about efforts to combine electromagnetic metamaterials with phononics. It's not quite the same thing as Foxonic metamaterial, but it's important research in that in that direction. So here you see split ring resonators. Actually, this work was done. I was a member of this collaboration. We did this work where we had split ring resonators, which are nanoscale, and hit it with an optical pulse. So it's like modulating the properties of an acoustic an optical metamaterial with acoustic waves, which is not the same thing at all as a Foxonic metamaterial, but at least it combines acoustics with electromagnetic metamaterials. And this was also done with split rings, but in 1D split ring type geometries. But this is not what we're really looking for. We're looking at, we want to find a decent acoustic metamaterial at the same time as the optical metamaterial. And this is how I usually try to present the concept of an effective mass mathematically. I take the example of an undergraduate example of a rolling cylinder subject to an applied force and a backward frictional force when it's on a slope. And if you do the sums from your undergraduate course, you find an acceleration, which is the force that's pulling it downhill, the component of the gravitational force downhill, divided by an augmented mass, which depends on the moment of inertia. It's a bit more than the actual mass. So it goes a bit slower than you'd expect if it was just an ice, a hockey ice puck rolling down a slope of ice. It goes slower because some of the energy needs to be stored in the rolling cylinder, in the rotational degree of freedom. So we define the effective mass as the applied force, which is the one that's just apparent. It's not the actual one that we call the hidden force, which is the frictional force, divided by the acceleration. And so the effective mass here is larger than the real mass. But you can actually find a formula for the effective mass by writing the acceleration as the total force divided by the mass. And you find that the effective mass is the actual mass divided by 1 plus the hidden force divided by the real force. And if the hidden force is smaller than, is negative, if the hidden force is negative, then you can have, for example, almost infinite effective mass. And if it's beyond a certain amount, then you can have negative mass. So you can have positive or negative mass. And the most interesting example for metamaterials, of course, a resonator. And if you calculate the hidden force, here you have an applied force on a mass, and you call this the spring is a pulling with a hidden force. It's connected to a wall, and you put in the same sums. The effective mass is now frequency dependent. And obviously from this equation, from the resonant frequency omega 0, which is related to the spring constant and the mass, according to the value of frequency you choose, you can get at low frequencies negative mass, on resonance zero effective mass, and at very high frequencies normal behavior. This is a component of, if you like, of a metamaterial. So it shows that if you plot the mass as a function of frequency, you can have negative or positive or zero from this graph. And if you want to make a metamaterial which is either, right, the simplest one could be 1D instead of just a meta atom. You can make a mass within a mass, like the one I showed you. If you apply a force at one end, at low frequency, you can get normal response, which is just like a wave going down the line. Above the first resonance, you get absorption. And this is effectively what happens when you have a negative density. And it's like a band gap. It is a band gap. And at higher frequency, you can even get extremely high phase velocity, where they're almost all moving together. So this kind of metamaterial is clearly an acoustic metamaterial. And so if you want to make an acoustic metamaterial, you should put a mass within a mass. And this is a hint on how to make a Foxonic metamaterial. You take an electromagnetic metamaterial, you don't really care how it worked, but you try and put a mass inside it in each unit cell, and then you, lo and behold, you have a Foxonic metamaterial. And just to come back to the same example of the mass within a mass, I said there's a band where the waves are damped, and that's the negative density band, which is predicted here when you have frequency on the vertical axis as a function of density on the horizontal axis. In this region, the waves don't propagate. Phase velocity is imaginary, and dispersion relation looks a bit like this. It's like repelling branches here. Okay, so this is very nice, theoretically simple. And I showed you this picture of the meta atom. So let's think about this meta atom when we want to make a Foxonic metamaterial. Now, the thing to do is, when you want to do this, is not to work in the optical regime, because everything is too tiny and nanoscale and very difficult to control. And so, by chance, I met Professor Tetsuya Ueda from the Kyoto Institute of Technology, and he had actually made a double negative impedance matched, not just double negative, but negative epsilon minus 1, mu minus 1, almost like the real Pendry original proposal for a flat lens. And not only that, it was impedance matched, so no reflection from it. And he managed to do this by this geometry of unit cell, which is a high dielectric constant disk surrounded by low dielectric constant epoxy with a thin copper mesh on top, which provides some of the negative permeability characteristics. And so does the fact of having a very, very high dielectric constant. And this thing works a real treat. Actually, this type of very, very high dielectric constant disk inside a lower dielectric constant medium was proposed earlier by other groups, Holloway here and Zhao. This is a review paper, but this is well-known technique. So what Professor Ueda managed to do was produce a really working example of this, and actually did the experiment with 5 layers, a flat lens with a source here, an observation area here. It was shown that you could get you could get focusing. Let's not say sub-wavelength, because never really works as well as you expect it to because of losses. But anyway, a little bit less than lambda spot size. Okay, lambda over 2 spot size. Anyway, it's a flat lens. It's focusing very nicely with epsilon equal -1, mu equal -1, and a transmission at the frequency 11.4 gigahertz, which is almost zero loss. This is a big achievement. So here is their unit cell, copper, ceramic, and epoxy. And as I said, we're going to try and make this into an acoustic metamaterial without spoiling its electromagnetic characteristics. And how are we going to do that? We're going to just shave off a little bit of the epoxy and replace it by silicone rubber. 0.4 millimeters of silicone rubber around the edge. And I'm talking about real materials, but I'm talking about not doing the experiment, doing this using finite elements, because first you have to design it, and then later you should make it. And silicone has well-known dielectric constant and loss tangent, and also well-known acoustic properties, which we know. So what are the acoustic dispersion characteristics of this new and old unit cell? So before adding any silicone rubber, it's a mess. It's just a phononic crystal, obviously, because it's a periodic structure. So you cannot call it a Foxonic metamaterial. However, marvelously, when you put this silicone rubber around each unit cell, you don't touch the metal layer, then you get a metamaterial gap opening. And the frequency of this gap is exactly the right frequency you expect from the mass of the object inside the unit cell moving backwards and forwards with the thin rubber layer between unit cells acting as a spring. And so this is a Foxonic structure, basically. Provided it retained its electromagnetic metamaterial properties. And to find that out, here is the electromagnetic simulation geometry with this silicone layer around it. And if you take, for example, 5 cells or infinite cell number of cells, you can do transmission. I'm not going to call it experiments, but transmission simulations, or you can do dispersion relation simulations. And to get the dispersion relation of this, first, the electromagnetic properties were found to be preserved. In other words, this is what you found without the silicone rubber. It really still works. So you have this TE mode. If I go back, I don't want to bore you with the details, but the electric field has to be in this plane, this TE mode, and splits into 2 branches, left hand and right hand. And at the right frequency, which is around here, 11 point something gigahertz, this is microwave. This thing shows those properties we want, which is negative mu and negative epsilon. In fact, the magic frequency is about 11.7 gigahertz. Okay, I didn't prove to you. I have to prove to you, of course, later, not in this talk, but I have to prove to you what the effective epsilon, effective permittivity, and effective permeability mu are. But just by looking at the dispersion relation, nothing changed. Why do I say nothing changed? Because firstly, this is the lossless dispersion with silicone, and if you compare with the non-Foxonic structure, when you have with silicone, in other words, and without silicone, even the transmission properties are still good. So this red curve is the transmission. So even with the silicone, the electromagnetic transmission is hardly affected. So this is also good news. So it is still working. Okay, but how do I prove to you? I have to go right back to the previous curve and show you the dispersion relation here. And you have 2 bands, and it's exactly the same, the left and the right hand band. And here you just have a very minor change owing to the extra silicone. So it's expected that this will work very well. And even when you include the loss of the silicone, it only adds a tiny bit of decrease in the transmission coefficient. In fact, 0.4 dB per cell of electromagnetic losses are incurred, but this is not drastic, so this is okay. And just to prove to you that there's a backward wave, which is almost as good as showing you the effective epsilon and mu, at this frequency we did a movie, And you can see that if you look at the phase, it's varying according to a wave that's moving contrary to the direction of your input wave. So this is 5 unit cells. Waves are coming from this side, but the phase velocity is going the opposite direction. So this is clearly a double negative electromagnetic metamaterial still. Okay, let's come back to the acoustics. There's a negative rho, okay, negative density, and there's a metamaterial gap. That's for sure, because the frequency is right. But just by chance, if you look below the gap, you can also find a backward wave, which is interesting. I'm not saying this is double negative. I'm just saying it's a backward wave. Just like you can get in a phononic crystal, you can have backward waves. Doesn't mean you have double negative parameters in acoustics, but it does mean that it's an effective negative refractive index, which can occur, as I mentioned, either by phononics or by metamaterial effects. Here it's phononic, but it's a backward wave. The wave is coming this way, and you see that the wave is coming backwards. Why are these two simulations different? Because here we're just showing what's happening without the silicone, and here we're showing with the silicone attached. You might not think this is very convincing for a backward wave. So this is not very convincing because this is an eigenmode. But to do a backward wave, you need to take like what we did in electromagnetics. You need an input wave, a region where there's a Foxonic crystal, and then a region where there's no Foxonic crystal on both sides. Then you can check which way the wave is entering, and then seeing which way the wave is going inside the material. This is 8 unit cells, 0.9 kilohertz, which is just below the gap. And if you look at the light blue curve, although there's not a single mode, it's predominantly going backwards. Okay, so it's a backward wave. So we achieved, in summary, negative refractive index in electromagnetics and negative refractive index in acoustics, but we didn't achieve quadruple negative because we have only a single negative acoustic metamaterial. So if you like, it's a triple negative Foxonic metamaterial. So in conclusion, we propose a realistic design of a Foxonic metamaterial by incremental modification of a double negative electromagnetic material. By use of a soft layer around a hard resonator, allows a single negative acoustic metamaterial to be added in a perturbative fashion. So we produced a triple negative Foxonic metamaterial with a negative mu, epsilon, and rho. What's missing is negative B. So don't let the people fool you into saying you've got a quadruple negative just because the thing happens to be negative refracting. That wasn't because of double negative acoustics. That was because of a branch with negative group velocity, which is totally different. So what we're doing is trying to achieve of course, a quadruple negative Foxonic metamaterial would be great. But to do that, we need double negative electromagnetic plus double negative acoustic. What we have now is double negative electromagnetic, but in this region, just negative density. What can you do with a quadruple negative Foxonic metamaterial? Good question. This is just what you do when you want to get grant money. You have to produce some possible application. Well, you know, flat lens works with a double negative material. So your optical source here is focused through a material, flat lens, and you have a focus point here. And at the same time, you have an acoustic source, which is focused, for example, in a different plane to the same point, and then it could come out here. And because you're focusing nicely here, you could possibly modulate the optical output if it was in the optical regime. Okay, so I'd like to conclude there, and thank you very much for your attention. And since I first presented this Phosonic work online at the conference of antenna in and electromagnetic systems in Marrakesh, I will conclude by saying shukran, which means thank you. Okay. I hope you're still here and not. Yes, you're still here. Okay.
At least I'm still here. So thank you very much.
Thank you.
Thanks, Oliver. It was really nice talk. Thank you. To the really interesting topics. So, I guess that we have some time now for discussion. If someone wants to ask something, just say something or just chat, and then I will give you the word. But feel free to comment anything you want.